Hello students. In the previous video, we learned about the cathode ray experiment and how it led to the discovery of the electron. So today what we'll do is we'll look at how Sir J.J. Thomson ingeniously used the same CRT setup to actually estimate the ratio of an electron's charge to its mass, also known as specific charge. So how did he do that? We saw earlier that an electron beam continued to travel in straight lines until it is acted upon by an external field. So let's see what forces begin to act on the electron in the presence of these fields. For this, we will have to use two relations that you will study in detail later in class 12th physics. When a uniform electric field is applied on the electron, an electrostatic force whose magnitude is given by F is equal to QE begins to act upon it, where Q is the charge on the electron and E is the electric field intensity. Force due to magnetic field is more interesting. Its magnitude is given by F is equal to QVB, where Q is the charge as before, V is the particle velocity, and B is the magnetic field strength, but it always acts perpendicular to the direction of motion, which means it never changes the speed, it only changes the direction of motion. But besides these forces, don't we also have gravity? So why aren't we considering it here? We'll get the answer in a couple of minutes. So back to the experiment. Thomson essentially varied these electric and magnetic field strengths and studied the forces and the particle deflection due to them. He argued that the deflection increases when either we increase the magnitude of the charge on the particle, increase their field strengths, or reduce their mass. Let's study this in more detail. Let's say we apply a uniform external electric field. In that case, the force and hence the acceleration of electron will be uniform. Do we know any other instance of body experiencing uniform acceleration? Of course, the projectile motion under gravity. So in this case as well, the electrons will follow a parabolic path. So let's say if the length of the electrodes is L and initial horizontal speed of electrons is V, then we can compute the displacement y as the electrons cross the field region. So here we suggest you pause the video once and try computing y yourself. Since there is no acceleration in the x direction, the horizontal velocity v will stay constant, so time inside the field region t will simply be L upon v. And in the y direction, since the acceleration is constant, we can apply our favorite equation of motion s is equal to ut plus half at squared. And substituting the values, we get the y deflection as half qe by m into L by v whole squared. And rearranging, we get the charge to mass ratio q by m to be 2y v squared by el squared. Are we done yet? We can surely measure the y deflection or the electric field that we applied, but how do we get an estimate of the velocity? That is where the magnetic field comes in. What if we align both magnetic and electric fields such that forces due to them act in the opposite direction and we tweak their magnitudes such that they balance out, resulting in net zero deflection? When that happens, QE will be equal to QVB, and hence speed of the electrons will simply be E upon B. Plugging this value in the above equation, we can compute the charge to mass ratio, also written as E upon ME. So using similar calculations, Thomson was also able to determine this E by M to be approximately 1.76 into 10 raised to 11 coulombs per kg. This was a huge contribution at that time, since it showed how light the electron is with respect to its charge. And now do we see why the effect of gravity would be negligible? So to summarize, Thomson argued that the ray's deflection increased if we either increase the charge on the particle or the intensity of the fields, or if we reduce the particle mass. And by conducting accurate experiments with varying electric and magnetic field, he was able to estimate the charge to mass ratio of the electron. And this value showed that the atoms are not indivisible and they contain very light negatively charged particles called electrons.